Hi students, today we are going to see design of Butterworth filter. So here design of digital filters from your analog filters. You have to map the desired digital filter specifications into those of an equivalent analog filter and derive the analog transfer function from that analog prototype, then convert it into its digital transfer function using the techniques. So your Butterworth filter has a low pass filter as a magnitude response of h of j omega equal to a divided by 1 plus omega by omega c power 2n power 0.5. So you'll be having your prototype as low pass filter. From your low pass filter, you'll be converting into an low pass filter of desired cutoff frequency or high pass band pass or band stop. So here where A is nothing but the gain of the filter, omega c is nothing but your 3 dB cutoff frequency, and n is going to be your order of your filter. So the magnitude response gives you this way. This is going to be the ideal response, and then if you're going on increasing your value of your n, that is the order of your n filter increases, you'll be getting your more appropriate response here. So normally your Butterworth filter are going to be or all pole designs will have your poles here. So it's going to be an all pole designs and maximally flat origin. You'll be having your flat origin. And at omega c, the normalized Butterworth filter will be of 0.07, that is your minus 3 dB. So will be less than that of your maximum value. And here the magnitude is monotonically decreasing of your function omega, and the magnitude response approaches to your ideal value when your order of the filter get increases. So these are the properties of Butterworth filter. Now we'll see the general procedure to design your Butterworth filter. So step-by-step procedure. Normally your general form of your Butterworth will be given as AP less than or equal to modulus of h of omega less than or equal to 1.0, 0 less than or equal to omega less than or equal to omega p, and modulus of h of omega is less than of as, and omega s less than or equal to. So from this problem statement, 5 parameter is very important. You are going to fetch your 5 parameter before start doing your problem. So the first one will be your omega p. This omega p is said to be your passband digital frequency, and your omega s is going to be the stop band digital frequency. And this omega p and omega p is going to be the analog frequency of passband and stop band. Your AP is going to be the gain at your passband, and AS is going to be your gain at the stop band. Apart from that, you have to get your, suppose if they are going to give it in terms of dBs, your gain in terms of dBs, now it's going to be your alpha P and alpha S, that is nothing but your passband and stop band attenuation or ripple. The final one is going to be your T, which is nothing but 1 by Fs, where Fs is nothing but your sampling frequency. So while you're starting your problem, you have to get AP, AS, omega P, omega S, and then the T. So the step 1, you have your 7 steps. So step 1 is to calculate your omega P and omega S. So they ask you to design your digital filter, but the problem they'll be giving in your digital omega and omega P and omega S. So that should be calculated in terms of analog. So for this one, you have to get the procedure to convert your analog to digital, right? So if they ask you to use your bilinear transformation, the formula to calculate your omega p and omega s is 2 by t tan omega by 2. Suppose for impulse invariant, the formula to get your omega p and omega s is omega by t. So by this one, you'll be able to obtain your analog omega p and omega s. Step 2 is to calculate your order of your filter. So the formula to calculate your order of your filter is 1 by 2 log of 1 by a square minus 1 divided by 1 by ap square minus 1 divided by log of omega s by omega p. So your n value will take the next nearest integer, the next largest integer. So even if your n is 1.1, you have to take your value of n as 2, greater than or equal to. So it's not round off. You're going to take your next nearest integer. Point number 3, step number 3 is to calculate your cutoff frequency. The formula used is omega s divided by 1 by s square minus 1 whole power 1 by 2n. So if you consider your passband frequency, the formula of your omega c will be also equal to omega p divided by 1 by omega ap square minus 1 whole power 1 by 2n, right? So here your step 4 is to calculate your normalized transfer function. So you have two formulas for n is even and for n is odd. So for n is even, your normalized transfer function is product of sum k equal to 1 to n by 2, 1 divided by s square plus bk s plus 1. If it is odd, it is 1 by sn plus 1, product of sum k equal to n minus 1 to n minus 1 by 2, 1 divided by Sn square plus Bk Sn plus 1. So here your Bk value is given by your calculator should be in radian mode, compound mode as well as radian mode. Step number 5, to determine your unnormalized transfer function of h of s by choosing your appropriate type of filter. So if it is low pass, your h of s, your s should be replaced by s by omega c. If it is high pass, it's omega c by s. And for low band pass and band stop, the formula is given in your frequency translation, analog frequency translation. Step 6 is you have to determine your digital transfer function h of z using your chosen transformation from your problem statement. If it is bilinear, you have to use your bilinear or your impulse invariant. Step 7 is optional. If they ask you to realize the transfer function using a suitable structure, you can realize, else it's optional. Now we can solve problems here. Here in this design procedure, they have you have four different varieties here. Standard one, either they ask you to solve using your bilinear or the impulse invariant. So you can see the problem for n is even as well as n is odd. Number two is they might give you the parameters in terms of dBs here and how to convert it into a normal one and then how to do the problem. Fourth one is apart from your prototype low pass filter, if they are going to ask any other filter, for example, high pass filter, how to solve the problems here, right? And the last one is going to be your analog filter. So analog filter design, out of this 7 step, only 4 step is needed. That is step number 2, 3, 4, and 5. You might get your analog filter, right? So we'll see an example in each. So here the normalized transfer function, you can by got till your order of your filter as 6, you can by got your normalized transfer function instead of substituting it in your formula here, right? So for n is 1, 2, 3, 4, 5, and 6 here, right? Okay. Next is your uh, problem. So design a digital Butterworth low pass filter for the desired specification using impulse invariant. 0.8 less than or equal to h of j omega less than or equal to 1.0 and 0 less than or equal to omega less than or equal to 0.2 pi and modulus of h of omega less than or equal to 0.2, 0.6 pi, 6 pi less than or equal to omega less than or equal to pi. So this 1.0, this 0 and this pi is going to be constant for all the problem. So from this one you have to check it's a Butterworth because you have your Chebyshev too. So you have to make sure it's a Butterworth and what they ask you to design. Here they ask you to design a prototype low pass filter. And number 3 is you have to just check what the technique they ask you to use to convert your analog to digital. So it's your impulse invariant technique. As I told earlier, you have to grab 5 parameters from your problem statement. So what are the 5 parameters? AS, right? So AS, AP. So AP is going to be 0.8, AS is going to be your 0.2, omega P is going to be your 0.2 pi, and omega S is going to be your 0.6 pi, and T is equal to 1 sec. Remember, the first your problem statement will have two lines here. First line deal with your passband, second line and frequency. This is stop band gain and this is your stop band frequency. So this is going to be your parameter. Apart from that, T here they didn't give anything about your T such as your T will give you the time period. So now we'll apply the procedure blindly. So step 1 is to calculate your omega P and omega S. This one, what technique they ask you to use is going to be your impulse invariance. So the formula for omega by T. Your omega p and omega t is substituted in the formula, and then your omega p and omega s is obtained. In your calculator, you just keep your calculator in radian mode. So zero point 0.2 into pi divided by 1 will give you the omega p, and similarly omega s. Step 2 is to find your order of your filter. So calculate your order of your filter with the formula 1 by 2 log of 1 by a square minus 1 divided by 1 by ab square minus 1 whole divided by a log of omega s by omega p. So this is how I have substituted the value of your as, ap, omega s and omega p. So now take your calculator. Whatever I'm just repeating, here, right? So don't think this is going to be a huge function. You can type it in one stretch to get your answer here, right? So take your calculator, keep your calculator in radian mode, log, open bracket, another one, open bracket, zero point 0.2 square inverse minus 1 close bracket divided by open bracket 0.8 square inverse minus 1 close bracket, again one close bracket, divided by open bracket 2 into log open bracket 1.8849 divided by 0.6283 close bracket, again one close bracket. If you press equal to, you will get your answers. So here 1 divided by 0.2 square can be read as 0.2 log open bracket, again one open bracket, 0.2 square inverse minus 1 close bracket divided by open bracket 0.8 square inverse minus 1 close bracket, again one close bracket, divided by open bracket 2 into log open bracket 1.8849 divided by 0.08. So as I told earlier, your n should be taken as next largest value, that's going to be your 2. The order of your filter is 2. The third step is to C omega c, but the formula omega is divided by 1 by a square minus 1 power 1 by 2a. So by substituting your value, you'll get this one. So use your calculator. 1.8849 divided by open bracket 0.2 square inverse minus 1 close bracket power 4 inverse. So if you press your equal to, you get your omega c as 0.8516 radian per second. The step 4 is to get your normalized transfer function of your analog filter. So here n is even, so n is 2, so n is even. So h of s, you just write the formula, and from the table of column you can pick your h of s as 1 divided by s square plus 1.414 s plus 1. Else if you substitute your formula k equal to 1 to n by 2, that is 2 by 2 is going to be 1. So k value is going to be 1. If you substitute your bk value, bk is nothing but b1. If you substitute it in the formula, 2 sine 2 minus 1 pi divided by 2 into 2 is 4. If you substitute, you will get your value as 1.414. So the value is going to be same. Step 5 is to obtain your unnormalized transfer function. So here unnormalized transfer function is obtained by replacing your h of s in h of s as s by omega c. So what happens if I replace your s as s by omega c, and then if I solve this one, take your LCM in the denominator, and denominator will go to the numerator. So it will be of 0.7252 divided by s square plus multiplication of these two will get you 1.2402 s plus 0.7252. So now your h of s is obtained. Now the next step is to get your digital transfer function. So here your impulse technique you have to use. You have to check your denominator can be factorized or not. If I'm not able to factorize my denominator, the left out choice is either it should be of s plus a divided by s plus a whole square plus b square, or b divided by s plus a whole square plus b square. But since your numerator doesn't have any s term, so your default choice will be b divided by s plus a whole square plus b square. Because for this term alone, I have your formula here. But I don't know what is your A and B from this one. So let us find your A and B here. So I take the denominator and equate it to s plus a whole square plus b square. This is the form I have to express. So if I expand this x plus a, s plus a whole square plus b square, so a square plus 2as plus a square plus b square. Now I'm going to equate your s 1.2042 is equal to 2a. So from this one I can find my a. And then I'll be equating my constant term. So a square plus b square is equal to 0.7252. And I know you my a value. So b square equal to 0.7252 minus a square. And then I'll be getting my b square. If I take your square root, I'll be having my b. So normally students will forget about this taking your square root. They'll be taking your b value as 0.3627. So you should be very cautious and conscious enough to find your b value. So now I can write your 1 divided by a square plus 1.2042s plus 0.7252 as s plus a whole square plus b square, and this denominator is 0.7252. Now I have the formula for b divided by s plus a whole square plus b square, but the b value is 0.6022, but I have some other value. So I have to make my b value. So I'm just multiply and divide your b value so that this original value may not change, right? So here what happens, I know that a divided by b can be written as a into 1 by b. So using that fact, I'll be separating this one 0.7252 divided by 0.6022 into this numerator. So the division of this one is nothing but 1.2043. Now I got b divided by s plus a whole square plus b square. By substituting my a value, b value and t value, I'll be able to get your, in the formula, I'll be able to get my values here. So here what happens here, I get your values as 3.3103 z inverse divided by 1 minus 0.206 z inverse plus 0.299 z power minus 2. So we shouldn't forget to multiply this factor. Normally students will forget about this one. So I should multiply this one. So if I multiply, I get my h of z as 0.3737 z inverse divided by 1 minus 0.9026 z inverse plus 0.299 z power minus 2. So now I got the digital Butterworth low pass filter for the specification Q. So we'll go for the next problem with your bilinear technique. So till your step 5, the value is the step is going to be same. First step and sixth step is going to get varied. Sixth step, you have to use your h of s. In that one, replace your s by 2 by t 1 minus z inverse plus 1 plus z inverse. You'll be able to get it. So first one, this is a problem statement. So from the problem statement, I have to get your 5 parameters: a, p, as, omega p, omega s, and t value. So 1 by root 2, that is your 0.707, and as is 0.2, your omega s is 0.45 pi, and your omega s is 0.65 pi. Your omega p is 0.4 pi, and t is going to be 0.5 second that they have given in the problem statement. So first step is to calculate your omega p and omega s. Since they ask you to use your bilinear transformation, the bilinear transformation formula is omega equal to 2 by t tan omega by. Substitute your omega p and omega s value in this one, and to get your analog omega p and omega s. So I repeat, keep your calculator in your radian mode. So your omega p and omega s is obtained here, right? The step 2 is to get your get your order of your filter, and you have the formula for this one. And substituting your AP, AS, and omega p, omega s, I'll be getting your value. So log open bracket, another one open bracket, 0.2 square inverse minus 1 close bracket divided by open bracket 0.7070 square inverse minus 1 close bracket, again 1 close bracket divided by open bracket 2 into log of 6.5247 divided by 3.4163 close bracket, again one close bracket. You will be getting 2.4538. So 2.4538, have to take your n value as 3. You shouldn't round off. If you are going to round off, the value is going to be 2. So here you shouldn't round off. You have to take your next largest value. Even if your value of n is 2.01, you have to take your n value as 3. So step 3 is to get your omega c. Omega c is omega s divided by 1 by a square minus 1 power 1 by 2a. So by substituting the value, I'll be getting your answer as 3.8433. Okay. Next, your step 4 is your determining your normalized transfer function for n equal to odd. The normalized transfer function formula is this one with your same bk. Right, so I'll be substituting your value, and then I'll be getting your answer as 1 divided by s plus 1, s square plus s plus 1 here, right? So here you substitute your bk value, that is bk value 1, 1. So 2 sine 2 minus 1 pi divided by 2 into 3, that is your 6. You'll be getting your value here. Right, so now step 5 is to get your non-normalized transfer function. So in your h of s, if you replace your s by omega c, you'll be getting your answers here, right? So I'll be replacing your s, where and all I have s in h of s, replace it by s by omega c, and then I'll be getting this value. So finally your h of s, by substituting the step-by-step procedure, you'll be getting your h of s, right? Now, step 6 to get convert your h of s into h of z. Here they ask you to choose your bilinear transformation. So where and all you have your s, replace it by 2 by t. 1 minus z inverse divided by 1 plus z inverse. I'll be able to get my h of z. In one single step, I'll be able to convert all my s term into z term. But I have to substitute it to the solve the expression. So here to do this problem, you should be expert in solving your expressions here, right? So I'll be substituting my t value as 0.5. So 2 by 0.5 is going to be 4. And then I'll be solving your, taking your LCM in the denominator. Denominator will be numerator. Then I'll just removing my uh, substituting my formulas a plus b whole cube and a minus b whole cube, and I expand this one to get my value, and then I just solve equations here, right? So normally your h of z in your IIF filter, the first term of the denominator should be 1. So I'll be taking that value commonly out, and then if I take 56.769 to divide it by 33,361.9224, value is 0.1569. So I keep my numerator as such, denominator alone I'll be going, right? So now I have converted your h of s into h of z using your bilinear. The last one we'll see how to get your high pass filter, as well as if it is in terms of your dBs here, right? So here this is a high pass filter. High passes, high frequency signal will be passed. So from 0.75 7 pi to pi, the signal will be passed. Low frequency signal will be stopped. So we'll be getting your the point 0 to 0.35. It's going to be stop band, right? So I have to get your 5 parameters A, P, A, S, omega P, omega S, and then T value here, right? So T they have given here, they have given in terms of dB here. Have to convert this value. So here you know very well 20 log of x will be in terms of your right? So never mind about the sign here. You're going to take the value and then you're going to substitute it in this formula. So if I want to find the value of your x, so I'll be dividing it by 20, and if I take your anti-log, I'll be getting your x. So the formula to convert your dB into a normal value, 20 minus, 10 power minus y by 20 will fetch you your AS. So to get your AS, um, by 10 power minus 4.436 divided by 20 will get you your 0.6. Get your AS, again 10 power minus 20 by 20, it's going to be 0.1. And your omega P and omega S, here you have to get it into your low pass filter, because you are going to design your low prototype. low pass filter, then only you're going to convert it into your high pass. So for low pass, low frequency signal will be passed. So that will be your pass band frequency. So your 0.35 pi will be your pass band. High frequency will be stopped. So your zero point 0.7 pi is going to be your stop band frequency and T is going to be 0.1 sec. That is given in your formula. The remaining thing is going to be the same procedure here. So to first step is to calculate your omega p and omega s. Here bilinear technique to be used. So omega equal to 2 by t tan omega by 2. So they obtain the omega s and omega p by substituting your values of your omega p and omega s. Then your step 2 is to calculate your order of your filter. So you have your formula by substituting your AS, AP, omega p and omega s. You'll be able to get your n value. So n is 1.7267. So your next largest value is 2. And your third step is to calculate your omega c by substituting your omega s, a s, and n value. I'll be getting my omega c. Step 4 is to get your normalized transfer function. N is even, so get your normalized transfer function here. Right. Step 5, you get your unnormalized transfer function, choosing your h of s by replacing your s by omega c by s, because here they ask you to design your of your uh, high pass filter, right? So now I'll be converting it into a digital transfer function. So where replace my s as 2 by t 1 minus z inverse divided by 1 plus z inverse, I'll be able to get it. So t value is 0.1, so 2 by 0.1 is 20. Be getting your values here. So if I just solve my expressions, I'll be able to get my h of z. So you know it very well. The denominator of IIR filter, the first term should be 1. So I'm just taking your 7646 commonly out. So that I'll be able to 400 divided by 906.7646. I have converted my h of s. I have designed my digital Butterworth filter, high pass filter. Right, so this is the varieties of problem that can be asked. So in your analog design procedure, step 4, first you find your order of the filter, next find your omega c, then find your the normalized transfer function, and step 4, find your unnormalized transfer function that will give you your h. This part you have to stop. So by this, after obtaining this part, I have to stop. So h of s. So this is the way to get your analog transfer function. So these are the varieties of your Butterworth filter. So for further clarifications, log on to